All right, folks, thank you for joining today. We are restreaming a presentation delivered by Chris McCoy that we actually did in the Mayhem Summit last weekend. So, without any further ado, I'll introduce Chris McCoy. Thank you for joining us, Chris.
Thank you, Omar, and thank you, CDocs. It's great to be here. It's an honor, and appreciate it. All right, so I'm Chris McCoy. I'm going to talk a little bit about the Linux networking stack and how you can use it to set up man-in-the-middle sessions so you can intercept certain types of packets or certain types of traffic. This talk will be about Linux and not any other operating system like Windows. So if you're looking for that, sorry to disappoint you. But let's get started. My name is, I'm of course a principal engineer with Cisco's Advanced Security Initiatives Group. You may not have heard of us before, but if you've heard of Talos, we're very similar to that, except we're mostly inward facing. We do a lot of security testing on Cisco products and services. That can be anything from on-prem to the cloud. We do different types of pen testing, security evaluations, architecture reviews. Anyway, I've been doing networking for about 25 years. I've been with Cisco and ASIC for about 13 years. Before that, I was aspirant in the Air Force, and I'm CCIE as well, emeritus, excuse me. And you can follow me on Twitter at that address below. So we're going to talk about doing using Linux as a router and what exactly that means from the point of view of what a router is. So some of the people who are on this talk may have some background on routers and bridges, or you may not at all. So I'll talk a little bit about that as well. We'll talk about how you isolate the man-in-the-middle machine so somebody can't come back and get into your own services. Let's say you're using Kali Linux and you want to you don't want all of the services like the databases to be exposed externally or have those exposed in any way. So we'll figure out how to use the some of the tools that you have within Linux to isolate the machine. We'll use Linux as a one-armed router. What I mean with that is if you have one interface and Linux is coming in and routing right back out the same interface that it came in on. We'll talk a little bit about that. And then we'll do some demos, and actually the whole thing's going to have demos in, strewn throughout. But we're going to talk about how you intercept DNS using DNS mask, HTTPS using MiTM, proxy, and secure shell using Little Sniffer. And then part of this as well, we'll also do a little bit of interfacing and interfering with the interior gateway protocols like open shortest path first. And then where those situations where you can't change any kind of routing, we'll use Linux as a bridge. So you'll do everything completely at layer 2. So to get started, so you know what bridges and switches are. Many of you probably already know, but a bridge and a switch, they're both the same thing, except switches do the forwarding of packets or forwarding of frames, in this case, in hardware. Bridges are considered more of a software function, but they're both the same thing. What they do is they create a broadcast domain from a collection of individual LAN segments, and they segment out what are called collision domains. Collisions are something you don't have to worry about anymore. They're long since gone. But what's important to know is that switches learn, filter, and forward frames based on source and destination MAC addresses. And they can be internally partitioned using virtual LAN. So what that means is that blocks broadcasts and certain devices from communicating unless they're inside of a virtual LAN. And you can communicate that information externally using tagged frames, and Cisco calls those trunks. This is not really specific to Cisco. This whole talk is supposed to be more generic, but I'm just using Cisco as an example. What's important to note about routers is that on a bridge or a switch, you can pretty much broadcast out, and everybody else on that same broadcast domain will see that frame. With routers, they are the one. What they do is they actually create internetworks from groups of broadcast domains, and so these could be links or VLANs. They don't forward broadcast packets under normal circumstances, and hosts must be informed of the router's IP address on the link. This is called a default gateway, which we've all configured. And one of the most important things to know about routers is the way that they discover networks and the way they forward networks. But when routers use routing protocols to discover all the networks that are inside of your network, and they discover the subnets, the links, and the most specific route or the lowest cost metric wins. So when I say most specific route, I mean the one that has the longest prefix length. So if you have a /24 and a /16, the /24 will take precedence. And that becomes very useful for you as an attacker because you can do some things like, changing routing so that you could start setting up man-in-the-middle attacks. When you're setting up your lab, this is something that has worked for us, but we typically do it like this. We have, we'll structure our lab with, you have a public network. Let's say you're coming in as a pen tester on a public network, let's say across the internet. You'll connect into a jump host. Alongside the jump host will be some kind of a firewall or router to keep out, miscreants from getting into your network. And you'll have a clean network that's behind that. And that's where you'll run some of your common services like a console server so you can connect to equipment. This is what changes like an SSH session into a serial connection so you can connect into a front panel of the router or some device. And then behind that, you'll have your pen test hosts, and those can be running Kali Linux, or you can run whatever you prefer. And what's really interesting, though, is that you have this dirty network that's connected to your Kali Linux machine or your machines that you want to pen test. This is assuming that you're pen testing some kind of device like IoT device, or you're going inside, you're actually running against something physical. If you're doing something in the cloud, of course, it's the other way around. You're going to be facing out towards the public network, and you're going to be going over the internet to target something, let's say, in Azure or AWS. But one of the things that's important to note is if you're using something like a hypervisor, like VMware, ESXi, vSphere, if you're using OpenStack, a lot of these systems, they use virtual switches that are connected to your VMs, and those virtual switches can interfere with your testing. So the best thing that you could do is to use PCI forwarding, that's VTD, that's what Intel calls it, to place physical interfaces in your VMs. Another option you can use is USB. So if you're plugging USB into your laptop and you have a virtual machine that's running Kali Linux, you can map that USB interface into your Kali Linux box, and that makes that interface available for you to use and not having to worry about your internal networking that happens on your laptop. So I really strongly recommend that you use physical interfaces of connecting into networks, and don't try to do this across the virtual switch. So first, to start out, we're going to use Kali Linux as a router. And so one of the things that I'd like you to keep in mind is when you're doing Linux, please don't use ifconfig. Ifconfig is long since deprecated. It is not a good interface to use. And plus, on top of that, IPRoute2, which is its replacement, has the IP commands. And the IPRoute2 package has all kinds of really nice little features that you might not know about. Like, for instance, if you wanted a brief overview of all of your interfaces, you could type -br. If you want colors, you could type -c or -all for all objects. And this will give you all of the addresses and all of the interfaces that are on your box. And so it even shows your interfaces that are down and up. I mean, it's very, very useful. It shows all your IPv6 things, and it does this all in one line. And, ifconfig, it's probably something that you're used to, but really, if you get used to IPRoute2, it'll give you the information that you want, probably in the format you want it. And now, not only that, but there are all kinds of features that you're going to miss out on, like bridging and setting up links and setting up things like VXLAN, for instance. None of that stuff works with ifconfig. So I really strongly recommend you take the time to learn IPRoute2 and how to add routes and how to add addresses to your interfaces. And I have some demonstrations of that in a little bit, just because a lot of people just don't know this information, and it's good to know. So when you're configuring Linux, there are several different places that you can look to tweak things besides IP addresses and stuff like that. There's sysfs, which is under sysclassnet and the interface name. This is more oriented towards layer 2. For instance, if you're setting up a bridge and you want to do things like spanning tree or multicast forwarding or some of these really crazy things, that's usually done under sysfs. And then under that is procnet, and those are your basic network configuration status. This is, I wouldn't recommend it, but if you don't have tools like netstat, for instance, if you're inside of a container and you want to look at some of the information about your network and you just maybe you don't have IPRoute2 or you don't have netstat because you're inside of a container and you don't have any control over what packages are installed there, then you can use procnet, and if you know what to look for, you can find pretty much all the information you want. But probably the most useful is proxysnet, and that's the network protocol. It's the IPv4, IPv6 conf in the interface name. This is where your detailed configuration is for mostly layer 3 and above. That's where your configuration is, you know, your behavior of how you forward traffic, whether or not you send ICMP redirects, which we'll get into, those kinds of things. And these are all reflected by the network namespace currently in use. Now, what is a network namespace? Well, let's get into that. I recommend that when you're doing some kind of pen testing or where you're doing any kind of man-in-the-middle testing, that you isolate yourself using a network namespace. So normally what will happen is you'll have your host. If you're not logged into it directly through the console, you'll be secure shelled into it, or you'll be using something like VNC to get into your desktop. And that's where you coming in from the right-hand side. That's your out-of-band network. And by default, Linux has the default networking namespace, which you really don't have to worry about. It's just there. And then you can create new network namespaces like I have on the left, where you have the link under test. Let's say you're connecting to a device or you're connecting to a network. And what happens is when you set up a network namespace, you have a separate table of sockets. All of your listening sockets is completely clean. There's nothing in there by default. You have IP tables rules that you can set up, and you don't have to worry about anything interfering with your other network namespaces. Also, if somebody was to connect back through you and you just didn't have your IP tables rules set up properly, that's okay, because there's no processes listening other than what you've explicitly run. Now, of course, if you're running a web browser, then that means you have to run the web browser from within the network namespace to get anywhere with it. But really strongly recommend that you do that. And to set up network namespaces, you can't use ifconfig. You have to use IProute 2. And the command is IP network namespace or IPNetNS. And then if you type help, it'll give you all the information that you need to do. Like if you wanted to create your own network namespace, set some kind of information about it, identify it, look at all the process IDs that are in a network namespace. And then if you wanted to put a link into the network namespace, it's IP link set network namespace. So regardless of whether or not you're using network namespaces, you're going to have IPv6 that's going to be active by default. Now, I'm a networking person. I don't usually like to tell people to disable IPv6, but in the cases of where you're doing some pen testing, you want to be completely silent. You don't want some host or reaching out to you or feeding you routes, which you can do with things like, router advertisements. So let's say we want to turn off IPv6 stateless auto address configuration. That's Slack. If you've ever seen where your device comes up with its IP address by itself, it listens to router advertisements, finds out what the prefix is that's on the subnet or on the link. In this case, I'm using FD001041. Okay, then it can actually create its own IPv6 address on the host's part. If you're not familiar with IPv6, it's 128-bit addresses, and almost all link subnets are all usually 64 bits, excuse me, of host information, bits. So let's say we want to turn off that. You could turn off stateless auto address configuration. You do that. Anytime you do this stuff, you have to bounce the interface. Otherwise, you'll still have addresses on it. So you'll do set interface name down and then set interface name up. Or if you want to, you can completely disable IPv6. But in that case, you won't be able to add an IPv6 address to an interface, even if you want to. So there's ways of getting around through all of the auto address and auto configuration without completely disabling it where you can't put an address on an interface. So this is an example of setting up a network namespace. So to start out, we don't have any network namespaces on our host. This particular host has two interfaces besides the virtual interface. So we have a virtual interface, ENS3, and then ENS5. And we're going to put our ENS5 and ENS6, we're going to put those in the network namespace and leave ENS3 alone. And so those are actual physical those physical connections that are mapped into my virtual machine. I'm using OpenStack and I'm using some flavors to do this. And if we go into the network namespace, we exec n1 bash, that puts us in using the bash shell. And then you'll notice the loopback interfaces is down and all the interfaces are down, so we'll have to set those to up. And so now we're up and we're ready to go. But if you were to look at all of the addresses, we've got some IPv6 addresses that are configured that, well, there's an FD00 address that we don't want. So let's say to get rid of that, I'm not doing any IPv6 testing, so we'll look at the IPv6 conf ENS5. We're just going to disable v6. If you use sysctl, SYSCTL, it does the same thing. This is just using the proc file system if you're comfortable with that. So now you'll notice that our IPv6 addresses are all gone. So now we're going to do some things like ARP cache poisoning. Now this is a really incredibly old thing that people have been doing for a long time. It still works. It's amazing. If you're inside of a container, let's say you're a container and you're not privileged, by default, you typically have the Linux capability called it's called capnet raw, and that allows you to send raw or set up raw sockets, open raw sockets, and they do this so that you can ping. But it just so happens that you can open raw sockets to do anything, like, you know, ARP cache poisoning. So you can do this even inside of a container. It still works. It's still there. And so what that does is, according to ARP, the RFC of ARP, you can send an unsolicited ARP reply. This is called a gratuitous ARP. And all of the hosts that are on the same subnet can see this information stored in their ARP cache tables. And usually what it's used for is it's used if you have, let's say you had a host and you had to swap a NIC out, and so the MAC address changes. If you had no way of overriding that MAC address that was already in everybody's caches, then you could be down for up to 4 hours. So it's a good, it's not there for no reason. It's there for a reason. The problem is that anyone can get on the network and claim to be any IP address pair that they like. And ARP cache poisoning attacks use this to redirect traffic. So let's say in this example, I have a legitimate host that's 10.40.1.31. And I broadcast that out to everybody. You can send it either with a broadcast, or you can send it with a unicast frame that goes directly to a particular target. But in this case, the victim doesn't have its traffic forwarded to it anymore directly, even if it's coming from the router and it's supposed to go to that the victim, the 10.40.1.31, it's going to the attacker instead. The attacker can then intercept that traffic and forward it back out the link to the device that is supposed to be out there. And so this is, in this case, it's actually a one-armed router. We're becoming a router. We've added an address. Let's say we've added an address to this interface. And we look at that, and now you can see we have 10.41.100, and we do some ARP cache poisoning attacks against, let's say, the default gateway. And normally what would happen is the target would then, let's say we were ARP cache poisoning the default gateway. So instead of the traffic going to the router like it was supposed to, it would go to us, and then we have to forward the traffic back out the link after we've received it. And so this is called one-armed router behavior, where we're forwarding the traffic back out. And in case of this, normally what happens is, under normal circumstances with IP, if you route a packet back out the same interface that it came in on, you would send an ICMP redirect along with it. And it's supposed to be for the situation where you have more than one router on a link and the router has to forward it to another router. You could say, hey, in the future, don't send it to me, send it somewhere else. Well, we want to turn that off. So in the case of this, that's what normally would happen with an ICMP redirect. We could disable ICMP redirects to 0 and send redirects to 0, and that would disable that behavior. So you won't see those packets go out anymore. When we're doing interception, you don't want to do that. You don't want anybody seeing you're doing that. Okay, we're going to do something a little bit more complicated now. So instead of being a one-armed router, we want to get in the middle between the VLAN 3, which is, let's say, a core network that gets out to the internet, and VLAN 40, which is, let's say, it's a link that's inside a data center somewhere. Now, a lot of this does assume that you have control over your router or switching network, and that's not that hard to do in some situations. One of the things that you'll find out about routing, if you get into it really deeply, is that a lot of the stuff is stuck in the Stone Ages. A lot of these protocols were designed in the 70s, 80s, and sometimes the 90s, but really it's usually mostly in the 80s. MD5 is used pretty rampantly for securing things like BGP. and your routing, and that's even if you're doing some kind of security on your routing protocol. If you don't have, if you have an MD5, great. If not, it's just MD5, and you can probably attack it that way. Or the passwords never get changed on a link. They could, or they maybe share the passwords. It's the same thing as sharing passwords within an account. So it's not out of the realm of possibility to attack networks. And I want to expose you to this, and I want you to see how this would work and how you would do this kind of attack. So we have this existing network, and we want to attack these targets, and we also want to attack a target out on the internet. So how do we do it? Well, the first thing that we're going to do is, let's say we have these 3 targets that are on VLAN 40, and normally those would connect to a default gateway. And we're going to look at the switch configuration. Right now, if you look at the show interface status, this is on a Nexus 9000 switch, just if you're curious. And you can see that we have these interfaces called man in the middle that we're going to target, and that's what we're going to go after. And so the first thing we need to do is we need to isolate those targets onto their own VLAN. So we'll make a VLAN, let's call it 42 in this case, and then we'll forward all of the traffic that's going from VLAN 42 into our Kali Linux machine on ENS6, and then we're going to route it back out on ENS5. Now, we've got a problem. When we set this up, there's this other VLAN out there that's called VLAN 40 that's owned by that router that's at the top of the screen on the right-hand side there. So we need to somehow figure out a way of getting around that so that we can get the traffic forwarded, let's say from the internet, into the Kali Linux machine so that we can forward it onto the target. And then we have another problem now too, because the default gateway has now gone away, right? The targets are going to be out there and they're saying, hey, I can't get to my default gateway, I can't get outside the network. So let's figure out how we're going to do that. So the first thing we're going to do, if we look on that interface that we're capturing, you can see that there are a whole bunch of ARP requests that are all going to 10.40.1.1. And they're like, hey, who's out there? Nobody's out there. So what we have to do then is we have to set up that address on our, wow, I guess I'll just go through this again. So we have to set up an address. And so, of course, what we'll do is we'll use IP-adder. So IP-adder is what we'll do to add that default gateway. And it's okay that there is 2 hosts out there with 10.40.1.1. There's the original router. That's the gateway at the top of the screen. And then there's also this router, it owns that network, and there's also us that has that IP address, and that's all right. You'll notice that we can ping down to the targets, but we can't, and we can ping up, so that's fine too. So we're connected through VLAN 3, it just happens to be the different network that we're on, and so we need to set up a default route in our stack that points out to the rest of the internet, and we'll look at IP route, and you can see that's it there. So we still got this problem though. So we've got the state of the network. It looks like this. We have an existing VLAN 40 with 10.40.1.0 on the top of the network there. And then on the right-hand side, we've got this new network that's VLAN 42. And we need to somehow get that router to forward the traffic to us. And then that way we can do the man-in-the-middle attacks on things, right? So the way we can do that is by using a tool to subvert interior gateway protocols. Let's say in this case we're using ISIS, which is a protocol. If you're not in a service provider, you've probably never seen. But there is this really, really nice tool that's part of Cisco Modeling Labs, which I'm going to show you, or it used to be called Viral, which nowadays that's probably not going to go over very well as a name. They changed it. It's now called Cisco Modeling Labs. They just came out with a brand new version 2.0. And chances are, if you really, the only problem with Cisco Modeling Labs is it does cost money. So if you don't want to spend the money, you can use other tools like free range routing or Quagga, where you can advertise those networks and then route things on to its destination. But keep in mind, the most specific route, in other words, the longest prefix link, wins. So we're going to use Route M. And so the first to start out with, we're going to look at the router configuration that's on there. So we're just going to look at its routes. And if we look at 10.40.0.0 and we're pointing out this network, what does this actually look like? Well, we've got a directly connected we've got a direct connection to that port channel 41.40. And you could see that it's got a directly connected route, and then we've got the /32, which you don't have to worry about, but that's basically for the router itself. And so we need to somehow override this. But if you'll recall, metrics can't get any lower. They can't get any more attractive than directly connected. I mean, that's as a good a metric as you're going to get. So we need to be more sneaky about it. We need to send a more specific route. So to do that, we're going to use a tool called RouteM. And inside of here, let's say we don't know what routing protocols we're using yet. Well, let's go ahead and just capture. We can see that ISIS is running on this network, and we're getting hellos and complete sequence number packets and all those other kind of great things that go along with ISIS. And I've got a configuration for you here and RouteM. One of the things that's really cool about RouteM is it's statically linked. You could just copy the binary to wherever you need it. It supports all different kinds of routing protocols. It does BGP, ISIS, RIP, anything you can think of. And so I'm going to suck in a configuration for ISIS, and I'm going to advertise that just to show that this works. And if we look in, now we've got on our ISIS neighbors, we've got some legit neighbors, then we've got this weird neighbor that's sitting out there, this 1.3.12.02, and then anyway, that is our attacking machine. So we found out that ISIS didn't have, the way they configured it, they didn't have any passwords, and now we're able to advertise all of these networks. And so in this case, I'm just showing that you can advertise not just one. It's usually used for like performance testing when you're using RouteM, but you can do as many routes as you want. You know, you can overflow the thing or flood the thing. So in this case, we've got some /24s, but nothing more specific. So that 10.40.1 is still sticking out there, and we need to somehow get around that. So to do that, we're going to use the most specific prefix win. So we're going to go into router ISIS. We're going to just change that around a little bit. So now we can go to, what we'll do is where we're advertising that IP route internal, we're going to change that to 10.40.1.1 and do a /25, and we're going to send, let's say, maybe 2 networks. And so now what's going to happen is we have 2 routes instead that are going to be going out to our router, and we can go back and look at that after we bring the adjacency back up. And now you could see that the route is still there, the connected route. It's just now we've got a more specific route that is going to us as the attacker. That's the 10.40.1.0/25. And that is going to intercept all of the traffic to our machines. And so that is how we get ourselves into the mix and be able to forward the traffic. And one of the things also that you're going to want to do is you're going to want to set up forwarding. So IP forwarding is one of those things. Unfortunately, this is going to catch you. It's going to get you. It gets me all the time too. Right now, even though we're advertising the routes, we're not getting any packets through because by default, the device or the interfaces don't forward packets. So we need to set up IP forwarding, and the only way you'll know that's happening is by looking at netstat-s and see that invalid address counter ticking up. You're not going to see it on any other logs or in any IP table. It's kind of, you know, it's a bummer, but that's the way it is. So I'm just showing you that that's really there, and it's going to stumble you up. So you're going to want to turn on forwarding, and we're going to do this on both interfaces. We're going to do this on ENS5 and ENS6. And so now, if we go back and we try to ping again, just from a machine that's outside, you can see now that we are getting through, and we're getting we're now setting ourselves up so that we can attack. And if you look at the routing, well, we just do an MTR, that's my trace route, you could see that we are indeed going through 10.3.1.201. So that's our attacking machine, and you can see that that's happening. All right. So now that we've set ourselves up, we've done layer 2 and layer 3. Now we're going to set ourselves up to do layer 4 through 7. And I'm going to introduce you to IP tables. We've probably all seen it in the kernel. It's called net filters, and it has all these different components. Not only do we have IP tables, which a lot of you have all worked with before. If you haven't worked with IP tables and you haven't actually set things up by hand rather than using user UFW, user firewall, or firewall D, I really strongly recommend that you take the time to learn it because it's not very difficult and it's incredibly powerful. So going across the top, we've got EB tables. That's for bridging. and that's useful if you're doing bridging, of course. ARP tables, IP6 tables. So IPv6 has its own net filter, has its own IP tables. So that's a lot of time. That's kind of what happens is people will go through, they will set up IP tables rules, but they'll forget about IPv6, which is turned on, and they haven't set up any firewalling on it. So a lot of times we see it all the time, actually, on real world scenarios where you'll have IPv6 is going through a product and they didn't think about it. There is a brand, well, it's not brand new, but it's been around for a while. It's called NF tables or NFT. I would recommend that you do look at NFT, but NFT does not support the bridging NAT, which we're going to be using later on, which I want to show you. That particular feature is not there yet, but it's coming all the time. Contract next to NFT is the firewall. That's the stateful firewall that is inside of Linux, and NF tables, excuse me, NAT is also along with that. So you have contract, which is your layer 4 through 7 aware. That's your layer 7 aware. So it can actually see your packets going in and out. It has helpers. And anyway, that is going to be the primary tool that you're going to use to do man-in-the-middle attacks using Linux and not using any other tools. So you can use this to build your own tools. So inside of NF table or inside of NetFilter's IP tables, it's all very complicated, but usually it goes like this. You've got some kind of a pre-routing with NAT, then you go into some kind of routing decision. Anything gets forwarded and then goes to post routing and then goes out. Anything that goes locally goes through the input chains and then goes to the local process and then goes out if your process is speaking to the network. And this is beyond the scope of this talk, but you can learn more about this by going to some of these links below. I have links to everything, and this is also in my GitHub, which you can use to go back and look this up. So contract is the stateful packet tracking firewall. It's intimately connected with NAT, and the connection state can be categorized into the following states. So you have new connections, established connections, related is some kind of flow that is related to a connection that is already permitted. And that could be, for instance, if you're using some protocols like FTP, where you can get connections coming back in from the client or from the server to the client, or ICMP error messages. And anyway, also you've got invalid if you've got some weird state connections. Those are things you might want to drop. Or you can explicitly say, hey, I don't want to track this particular flow. And one of the things that's really interesting to note about IP tables is that once a packet flow is set up and it is established, it will completely bypass all the other rules. In other words, if you're looking at the counters for other rules, your existing flows will not be taken into account in those counters because they are completely bypassed. So what you can do is contract has some accounting that you can do to actually count packets or bytes or that kind of stuff. If you want, you could turn that on. But at any rate, let's take a look. So if we look at the IP tables, remember we're in a network namespace, so we have our own. We're looking at the forwarding table, and we're using the contract. And right now, even though we have packets that are going through us, we don't see anything. And those are getting bypassed. And so the way contract works, and by the way, you have to install this tool if you don't have it installed on Kali Linux. It's not there, so you have to do apt-get contract and or apt-get installed contract. That will actually install contract for you. So what we're going to do is we're going to set a contract rule up that's going to look for new connections. And from that point forward, now the firewall, the stateful firewall is working, and we can actually monitor it and watch the packets, watch the connections go in and out. And you could see kind of at a layer 4 level what exactly is happening in this network. All right. So if you wanted to look at some of the connections or some of the settings for NetFilter, you can go into ProxysNet, NetFilter. There's some configuration options in there, like the maximum number of flows, how strict you want to be with TCP, those kinds of things. All right. Now I'm going to talk about the real meat of the whole talk. If you get nothing else out of this talk, the thing that's important to note is that DNAT is the key. This is the thing, this is the tool that you want to use to intercept any kind of traffic, let's say DNS. In this case, we're going to use DNS masquerade or DNS mask. So the DNAT target. If you're familiar with iOS, that Cisco iOS is a router, the routing network operating system, they have this concept of inside and outside interfaces with NAT. So you have traffic that's flowing from inside to outside, and it gets mapped to, to inside global addresses. And anyway, you don't have to worry about any of that stuff with Linux. It doesn't have a concept of anything like inside and outside interfaces. You can even have traffic entering one interface and going out the exact same interface, and you can still do NAT. And the only caveat with that is that you have to somehow get the return traffic to come back to you when you're doing this one-armed NAT. And the way you would do that is through IP masquerade or using SNAT, and that's another feature. But really, what's key is DNAT, and that is the key tool. So if you remember nothing else, DNAT is the tool. And what DNAT allows you to do is it allows you to take a flow. You identify a flow using IP tables rules. It has to happen in the pre-routing chain. That's the only place where you can put it. And what you'll say is that any coming from this source to this destination, in this case, we're intercepting port 80, so HTTP, we're going to DNAT, and we're going to change the destination as it goes through us as Linux. And we're going to change that destination to another IP address on our network. It could be local, it could be remote, it could be anywhere. You can even forward traffic outside onto the internet somewhere else. You don't have to do DNAT on your local machine. You can actually forward the traffic somewhere else and do all the intercepting and the processing somewhere else. But from the point of view of the victim machine, it's going to look like they're connecting to who they think they're connecting to. They think they're connecting, in this case, to 10.3.1.15, and in reality, they are not. So DNS mask, it's a really simple, lightweight DNS server. It works great for doing man-in-the-middle. You've got command line arguments that you can pass to it saying, hey, I want to map this IP to this name, and it does it, and it takes care of it. It's really nice. And if it doesn't have an entry in its command line or in its configuration, it'll just use the local resolver. And so this is an example of how we do it. So first thing we're going to do is we need to figure out, okay, what are we using for DNS server? So let's say we're trying to figure out what the port 53 is. So we could see that, okay, this machine is using 10.3.1.15 as its DNS server, and we want to get in the middle of that. So we looked at that, we looked at contract, and now, so we're going to look at the UDP sockets that are listening. You can see that there are none. And if we look at the NAT table, we're going to go ahead and add a rule in the pre-routing chain. Okay, it has to be there. We're going to look for anything that's coming from our victim. It's going to 10.3.1.15, which is the DNS server that they're using, going to destination port 53, and we're going to NAT that to us. And we're going to use a different socket. Let's say we'll use port 1053. And so now, if we look at those rules in IP table, you could see that we've had 12 packets so far, and we haven't answered, of course, because there's nothing listening on that socket. So now we're going to set up a DNS mask. We're going to enable debugging, set it on a certain port, and so now you could see the connections that are coming out, the resolution requests, and you could see that they're going to things like cluster local. That indicates that they're trying to get outside of it, let's say a Kubernetes cluster, and that's actually leaking to the rest of the network. Or yeah, we could see exactly what's going on. And so in that case, there it is. If you wanted to redirect to something else, we could do it that way. So that's how you use DNS mask. And then for time constraints, I'm going to just start MiTM proxy. So we're going to do HTTPS interception using MiTM proxy. If you hadn't seen MiTM proxy, it's a great project. This works great. Let's say you're using, we're doing some kind of, let's say, machine-to-machine traffic, and you wanted to look at all of the flows that are happening. That's really what MiTM proxy is for. I mean, you could use things like Burp Suite, and that's great for local connections. You can also use DNAT to forward to Burp Suite if you wanted to. That works as well. But if you're constrained and you need to do a command line, MiTM proxy is wonderful for that. It decodes a variety of payloads. It even does web sockets and protocol buffers, Google protocol buffers. Those are used a lot more often. You'll see those in a lot more modern web applications. Strongly recommended. So anyway, to get it going, we're going to do the exact same thing. We're already intercepting DNS. So in this case, we're also going to set up ourselves up again. We're going to do another interception, but in this case, we're going to do TCP. We're going to match on multiple ports. So in this case, we can actually match either port 80 or port 443, and MiTM proxy doesn't care. It can actually take something that goes over TLS or something that's completely in clear text, and it'll just transparently handle everything. Now, in reality, there's still a problem here. We're not actually breaking TLS. I mean, if I could break TLS, I probably would be worth a lot more money than I am. But in the case here, we have the problem, right? We don't own the target. In this case, they're connecting to www.ciscoconnectdna.com. We don't have a certificate for that. So in the case of the, let's say in the case of the target, we can log into the target and we can replace that certificate. So what we could do is, well, not replace it, but we'll supplement it. So MiTM proxy generates a certificate authority cert, which we'll get into this in a little bit on what this means. And then we can actually put that cert on the target. So now it trusts us as a certificate authority. And so to add the certificate, we'll add it to the host trust store. So in the case of this, where we're the man in the middle, we've got, let's say we're going to www.example.com, and which in reality wouldn't have a certificate for it, at least it shouldn't. But in this case, we have actually issued that certificate from CAs, an intermediate CA, and eventually up to a root of trust. And we need to be able to get that connection in between. So that's what we'll do is we'll add our MiTM proxy certificate authority to the victim. In this case, we could just log into the victim, and you go to Etsy SSL certs. This is a Ubuntu-based machine. So what we're going to do is we're just going to concatenate to this file called ca-certificates.cert. And so that's what we're going to do here. And so we'll paste that in. And so now that certificate is now part of the trust store of the host. And so if we go back to MiTM proxy again, and we look and we're seeing what's going in now, you could see that we are getting connections through the DNAT entry. And so now we can actually look into seeing what's going on with this particular target. And if you wanted to, you can highlight a flow. You could see exactly what's going on. If you're doing let's say you're doing JSON, it can decode all that. It can decode all the things that's going on with TLS, the certificates, and any kind of the payload that you want. So it's really, really nice system. I think it's great. Right. So that's about how to do MiTM proxy. And so this is kind of a whirlwind tour. The next thing we're going to do is we're going to do some SSH interception with Little Sniffer. Little Sniffer is part of the DCEP proxy, which is a Cisco Talus project. It's a very simple Python proxy. It has no dependencies. But in the case of Little Sniffer, you do need to use Paramico, which is a tool, or it's a package that you can install in Python. And this could be used to MiTM SSH sessions and actually capture passwords. So if you use something, let's say you have a target, a victim that is going to be using, let's say they're using Ansible for their configuration management. I see this all the time. When people set up Ansible, they don't do strict host key checking of their destination. They have that turned off so that they don't get any errors, or if the host keys change. In that case, you might be able to intercept things like passwords. You might be able to intercept configurations that get pushed to a host. It does require that the connection for SSH is using password authentication. If you're using pub key auth, then this won't work, but it does work for password auth. So in the case of Little Sniffer, first thing we have to do is we'll set up our IP tables rules just like before, except in this case, we're going to flush the pre-routing table, pre-routing table. And so now you can see we have nothing. We're going to add another rule. It's going from port 22 to port 2222. One of the things you have to know when you're doing SSH is it's a one-to-one type thing. You need a listening socket for every destination that you want to intercept. So in this case right now, DCEP proxy doesn't have certificate, or it doesn't have a key, so you need to generate a key. In this case, we just generate an RSA private key that'll be used from the point of view of the victim. So if the point of the victim is using host key checking, of course we're gonna get caught. But if they're not, then, or if they just, if they just session right through, they say, okay, well, the host key changed. Oh, well, let's just delete it and start all over. Well, in this case, what we're doing is we're targeting something that actually is not doing host key checking. And by the way, this is fixed, but this was an original vulnerability that we had to go after, and we discovered. And you can see in this case, we actually intercepted the username and password that it was using to connect to a device, and we can actually see everything that's going on. So Little Sniffer is really useful for those kinds of interactive SSH sessions where you want to see what's going on in your network. All right. Next, we're going to talk a little bit. We're going to go back down. So we're up on the stack. We were doing TLS, we're doing MiTM proxy, and we're doing Little Sniffer. And so now we're going to go back down to layer 2 again. Let's say in the case of sometimes you don't have full access to the network, or let's say you want to just basically be a bridge. Let's say you have, let's say a little Raspberry Pi or something like that, and you want to bridge something from a USB connection that's going to a target, and let's say you want to go through yourself and go out somewhere. Linux will allow you to do that. It allows you to not only do bridging, but it allows you to do all of the DNAT things that I had showed you before. It actually will work at layer 2, so you don't have to worry about monkeying around routing at all. So first, to get started, we need to create a bridge. Linux uses this parent-child relationship between links, or master-slave, where you could stack interfaces into a hierarchy. And this can be used for multiple things. It's used for bonding, so where you're splitting one virtual link up to maybe multiple physical links. It's also used for something called VRFs, virtual routing functions. They are virtual routing forwarding. That's the separate routing table in the network namespace. Or more specifically, what we're going to do today is we're going to use bridging. And so to set up bridging, we have to create a bridge link, and then we have to make the other links think that the bridge is the master. So again, we're going to be using IP route 2. We're going to create the bridge. First, we'll create the bridge link with IP link add br whatever, or whatever you want to call it. We're going to give it a type of a bridge. We'll set it to up, and then we need to set the physical links to use the bridge as a master. And then now we have that hierarchy where you have your physical links going in. We have those slaved up to the bridge, and that creates a stub layer 3 interface. So you can put an IP address on the bridge interface itself, and as long as it matches the subnet that you're working with, everything's golden. It's all great. So to use net filters, we can use the DNAT target. The only thing is that we have to tell the bridge to call IP tables whenever it has traffic flowing through it. And so what happens is bridges, or the flows, will virtually terminate in the bridge, and a new connection will be made by the MiTM machine through the stub layer 3 interface. So you want to make sure that the subnet matches. And this happens as the traffic's getting bridged. So the victim, when it forwards the traffic on, it still thinks it's talking to whoever it's talking to, but in reality, your layer 3 man in the middle machine is doing the interception with DNAT and either forwarding it locally or forwarding it somewhere else. As long as the traffic flows back through that bridge, you're golden. Everything will work. The thing that you do have to keep in mind is that you do need to insert the BRNet filter kernel module. And so you use modpro BRNet filter, and then you could either set, when you set the bridge up, you can set a setting so that it does NF call IP tables, and what happens is that all traffic that flows through that bridge will go through and it will call IP tables, and you can do all the normal things that you would do even if you're even if you're layer 3. It has the same thing for ARP tables and then IP6 tables as well. So the link at the bottom, thornton.info tools mibr.html or HTM, that was the link that I saw that introduced me to this idea. So it's really highly recommended to go check it out. You can see exactly what they did. All right. So here's the resulting configuration. Just in this case, we've got the target that we're wanting to intercept. So we're doing, we're again using the pre-routing table. it's coming in on the bridge interface. It's going from this source to this destination, and we want to use DNAT to the destination shown below. And so from the point of view of the server, let's say they're using Google as a DNS server. From the point of view of the target, they think they're talking to Google. They think they're talking to 8.8.8.8, but in reality, they're talking to our MiTM machine, and then we're sending our connection out to Google, and it thinks it's talking to the stub layer 3 interface of the bridge. All right. So we're finishing up what we learned. So I'd like you to remember that you want to set up your packets or set up your labs so that packets can escape without you wanting them to. In other words, you have to go through not only your machine. So if let's say you have a target, if you're using network namespaces, that becomes a lot harder. And then you want to make sure that you use physical interfaces. So either you want to use those USB to Ethernet interfaces or use PCI forwarding or VTD. You know how to isolate your man-in-the-middle machine using network namespaces so local processes don't interfere. You got a clean IP tables and routing table. The key tool is DNAT. DNAT is what allows you to redirect sessions as they're coming in. If you wanted to change the source IP address, you can use SNAT or IP masquerade. That works as well. That'll actually really say, okay, the traffic is really going to come back using this IP address, and that might be useful if something's going to get routed some other way. But otherwise, DNAT is key. And then I showed you how to use DNS masquerade. It was very high level because of the limited time. But MiTM proxy is good to look for. SSH or Little Sniffer is a great tool for SSH. If you want to use Linux as a MiTM bridge, make sure you use brnet filter and use nfcall IP tables equals 1. All right, and you would use those anytime you didn't want to go screwing around with interior gateway protocols. But remember, RouteM is there. It's available for you to use if you have a license for what was called RouteM or what was called Viral, but now it's called CML, Cisco Modeling Labs. Or you can use something like Quagga or free range routing. That works as well as far as open source tools. All right. I guess if you have any questions, you can join the Red Team Talks channel that's on the Red Team Village Discord. That's at redteamvillage.io/Discord. The slides are available for you to use as well. If you wanted to look at these slides, it doesn't include the videos because the videos are kind of big and plus they don't have any information that you hadn't already seen in the slides. Also, I included a cloud init script that you can use, let's say in an OpenStack environment. It's a little harder to do man-in-the-middle when you're doing AWS, but cloud init is the exact same configuration. That'll help you set up a man-in-the-middle bridge, and it also includes things like VLAN, so you can do multiple targets at the same time. All right, I appreciate the time, and that's the end of my talk. And any questions, you can just get on Discord and ask away.
Excellent. Thank you, Chris, and thank you everyone for joining today. And this concludes.
All right, it's been an honor.
Thanks.